Have you ever considered why somebody's hair stands on end when there's an electric charge in the atmosphere? Or why those little iron filings make such nice lines around a magnet? This lesson is on field lines, starting the chapter on electric and magnetic fields. So, lightning occurs when warm air floats above cool, and that air starts to condense and release electric energy. As the warm air rises, electrons are transferred to the raindrops, which ends up creating a charge in the cloud. So the bottom of the cloud has a negative charge, and the top of the cloud has a positive charge. So there's a negative charge at the bottom of the cloud and a positive charge at the top of the cloud. As the electrons begin to move away from the cloud, this causes a charge separation. So the surface is then below the storm is going to become positively charged. The surface becomes positively charged, and below the surface becomes negatively charged. So on the ground. So the surface of the Earth is slightly negative, and then below that is positive because those like charges are going to repel. So if I go back, I can show you then. So then the very surface of the Earth has a positive charge, and below that will be negative. So lightning strikes when the electrons from the cloud are attracted to the positively charged surface. And this transfers a huge amount of electrons, like 10 to the power of 18. A coulomb of energy, which is the unit of energy, is 6.25 times 10 to the 18 electrons. And if an object transfers electrons, the charge is determined in coulombs, and this could be positive or negative. So lightning transfers huge amounts of electricity, which is why it's so dangerous. Looking at some other energy technology, terminology, one of them is a voltage. So if we want to describe the electric potential between two substances, like a static shock after we've walked on the carpet and then we reach for the doorknob, we want to talk about potential energy. So we have stored that electrical potential energy in our finger, and then it's converted to light, sound, and then also energy, which is why it hurts. We can determine voltage with the equation the change in energy divided by the charge, where the change in energy is in joules and the charge is in coulombs. So when we look at voltage, 1.5 volts is 1.5 joules of energy per coulomb. So it tells us how much energy is in that unit per its charge. So voltage is related to energy transferred per coulomb. So if there's a lot of energy, the voltage is typically high, like in transformer power stations. And lightning is dangerous again because the voltage and the charge are very large values. So when it comes to electricity, it has both forces and fields. So some basic matters that we accept as fact. All matter has mass. Energy exists in various forms like kinetic and potential. Everything in the universe is in motion, and changes in motion are due to forces. So forces that act upon an object to make it move or act upon an object to make it stop. And forces can also act by means of fields. So a field explains why two objects can affect one another even if they're not touching. So if you're trying to force two magnets together, they may or may not attract or repel. So in general, fields are spheres of influence, and they can be scalar or vector. So scalar fields have no direction, like sound and heat. So for example, the heat around a campfire generally is going to be the same no matter where you are. And no matter what the distance you are from an object that makes a sound, if you're the same distance, it doesn't matter what direction. However, some vectors like gravitational have direction, where the gravitational field pulls objects towards the center of the object. An electrical field is the space around a charged object where any other charged object will experience a force. And every charged object has a field that surrounds it. Forces may be attractive or repulsive, so like charges are going to repel, and unlike charges are going to attract. Magnets also create fields. The forces by magnets are both attractive and repulsive again. So like charges are going to attract or repel, and unlike charges are going to attract. Magnets do not create electric fields, they create magnetic fields. And magnets are not charged. They have poles, a north and south pole. So two like poles will repel, and two unlike poles will attract. So some metals called ferromagnetic substances have magnetic properties like iron, nickel, and cobalt. So inside these magnetic substances are tiny magnets called domains. And if the domains are all able to align, the material is magnetized. And if the domains are not able to align, the material is not going to be magnetized. When we draw an electric field that is created by a magnet, we draw away from the North Pole and towards the South Pole. So our field goes out of the north and into the south. And we use magnets for navigation in the work of compasses, to generate electric currents, and in motors. Gravitational fields have a space around a mass, and they change the space around this mass by drawing things towards the center of it. Two masses are able to exert gravitational forces on each other. So the moon exerts a gravitational force on Earth, and it gives us tides, and the Earth exerts a gravitational force on the moon, and we cause it to orbit us. Isolated masses are also able to modify the space around them, and then any object that enters that space is going to be being modified by that gravitational field. And the field will always point towards the most massive object. So if the moon is in the Earth's gravitational field, the Earth's gravitational field will be the one where the arrows point towards, where the field points toward. So here is how we would draw the gravitational field of Earth. So we have the gravitational field lines with the force going towards the center of the Earth. So in field lines, describe the direction of the field. Would be the arrow towards the center, and the more arrows, the stronger the field. So when we look at different field lines, we want to know if they're magnetic, gravitational, or electric. In magnetic, it always goes north to south. Gravitational is always towards the center of any object. And for electric, we're towards the negative and away from the positive. So the top ones are an electric field, so we're going away from the positive and towards the negative. The bottom on the left are magnets going from north to south, and then the Earth, which should be showing the gravitational field. Now that last diagram, we want to know which one's positive and which one's negative. So for an electric field, A is going to be negative because the field is going towards it, and B is going to be positive because the field is going away from it. So A is going to be negative, and B is going to be positive. I hope you enjoyed today's lesson.